Good morning, ladies and gentlemen. My name is Dung-Ting Tsai. Today, I'm going to talk about design and implementation of high-efficiency power inverter using adaptive nonlinear control. And today, we will introduce power inverter control design, simulation and experimental results. Conclusions. Finite nonlinear control law is based on adaptive framework optimization, we say AGWO, to uptrain high-efficiency power inverters. Through sliding mode control, we say SMC, is robust to some internal dramatic changes and external melting. The system state cannot converge to zero in finite time. FT-NCL still has the problem of jitter, which causes hermetic distortion of the output voltage of the high-efficiency power inverter to effectively suppress the jitter. The gain parameters of the FT-NCL can be ultimately adjusted using the AGWO algorithm. Renewable energy sources such as solar power, wind power, and biomass power have been widely used with the reduction of fossil fuels. Among them, power inverters are undoubtedly one of the essential devices in renewable energy sources. The output voltage weight of power inverters should meet the needs of encountering transitory and steady-state fluctuations with fast compensating capability and less total hermetic distortion. The equations of error state for the power inverter have the following expressions like this. This is our power inverter. It can turn AC to DC and use controller to control the voltage. This is the formula of FT-NCL. The sliding region can be structured as this. The FT-NCL is further embodied on the axis of power reaching low below this. This is the resultant FT-NCL control law. And this is control design. The target from here to be amended to here. Jitter exists in sliding manifold. The position of the gray valve surrendering the spoil is updated as this. It could reduce the jitter problem. The protection position is then renewed as this. This is simulation and experimental results. And this figure 1. This is proposed scheme under static change loading. And this figure 2 is classic FT-NCL static change loading. In the figure 1, cumulative output waveform of the proposed power inverter is plotted for a static change loading. A minor drop in output voltage is visual, and it is turned to the reference voltage within a short period of time. With this proposed scheme, there is an impressive tendency to mitigate temporary voltage drop. In the figure 2, the simulated output waveform of a classic FT-NCL power inverter under static change of load is seen. And this figure 3 is proposed scheme LC variation. And figure 4 is classic FT-NCL LC variation. In figure 3 and figure 4 clearly reflect that the experimental output voltage of the classic FT-NCL power inverter is sensitive and skewed, while experimental output voltage of the device's power inverter in this paper approximates to the sinusoidal shape. And conclusions. We introduced an adaptive gray-wolf optimized final time nonlinear control law for a power inverter, which is capable of generating less control waveform and quick transient and different type of loading. The major peculiarity of the final time nonlinear control law is the limited system state convergence time. Nonetheless, the jitter problem persists and worsens the performance of the power inverter. In this case, an adaptive gray-wolf optimization is employed to optimize the gain parameter of the final time nonlinear control law, allowing for improved transient and steady-state relations. This is our report. Thank you for attention.